Hello everyone, welcome to this video. In this video, we shall be looking at the proof of this result that I have presented to you in the previous video, right? So the result here tells us that the conjugacy class, it forms an equivalence relation such that the relation is defined like this: two elements A and B, they are related to each other whenever they are conjugates of each other. So that means B is equal to x A x inverse for some x in G. If you are able to find such one x which for which this relation is true, then we would say A is related to the element B. Right? So let's move forward on to proving this result. In order to prove that this is an equivalence relation, what we need to prove? We need to prove that this relation is reflexive. Next we need to prove that this relation is symmetric, and next we need to prove that it is transitive, right? So in order to prove these things, we go step by step. So first of all, we prove reflexivity. Now what is reflexivity? Reflexivity, we have to prove that the element is related to itself, right? So we assume we need to prove that A is related to A. So you can clearly see the proof is very simple. We assume A as some element present in G, then we may write A as the identity element multiplied with that element multiplied with the inverse of the identity element. There is no issue. We may write A like this. So it is of this form where this E is present in our group, that we already know because it is the identity. So therefore we can now say A is related to A, and this is true for all the A which are member of the given group, because we have considered A to be some arbitrary element. So therefore we have the relation this as reflexive relation. So this part is proof. Reflexivity is proved here. Next we need to prove the symmetry property. Now for the symmetry property, we assume that A is related to B, and we need to prove that B is also related to A. So the converse part. So now because we are assuming A is related to B, it would imply that we are able to write B as for some element x which is present in this group G, we may write this B as x A x inverse, right? This is given to us. Now in order to prove that this B is related to A, we need to prove that A could be written as x B x inverse, right? For some x present in G, it could be any member x which is a member of G, right? So here what we do, we consider this B, because we know this relation B which is x A x inverse. So from this relation what we can do, we can pre and post multiply with x inverse on both sides, and we can post multiply on both sides with x, so that here in the left hand side we would have x inverse B into x, right? This is what I have written. And on the right hand side we would have x inverse x A x inverse, x inverse x A x inverse, and then x, right? This is what we are doing here. Okay, so after pre and post multiplying, pre-multiplying with x inverse, post multiplying with x, we have this relation. Now using the associativity property, we have this thing, and you know some element inverse multiplied with that element would give you the identity, and similarly x into x inverse would also give you identity of the group. So therefore on the right hand side we have E, here we have A, and here also we have E, right? So that means this right hand side now becomes equal to A. So finally we have A as equal to x inverse Bx, and you can write this x as, the inverse of x inverse, correct? So therefore we are just rewriting it over here. X could be written as the inverse of x inverse. So now because we already knew that, by the assumption we knew that x was some element present in our group G. Now because x was present in our group G, so that means x inverse would also be present in G. Why? Because G is a group, and we know in a group the inverse of each of the element is present within this group. So therefore we have written this A as some element of this group G, and times B times the inverse of that particular element. So we have written A into this form So this proves that B is related to A, and hence we have the symmetry property with us. So we have the symmetry property with us. Next we wanted to prove the transitive property. Now what is this transitive property? Transitive property tells us that if A is related to B and B is related to C, then A is also related to C. So we assume that A is related to B and we assume that B is related to C. So we need to prove that A is related to C. So here, because A is related to B, that means we can write B as x1A x1 inverse, where what is x1? x1 is some member of the group G. And because B is related to C, so that means C could be written as x2B x2 inverse, right? Where x2 is also some member of the given group G. So from here, because we wanted to show this thing that A is related to C, what we do? We consider C, right? Because C is equal to x2B x2 inverse, so we are writing it over here. Then what we are doing, we are writing down the value of B here. The value of B is x1A x1 inverse, so we are writing it over here, and x2 and x2 inverse are as such, right? So then when using associativity, we are just adjusting these brackets so that we have x2 x1. Now what is this thing? x1 inverse x2 inverse. By the law of inverse, you know, you may write this as x2 x1 inverse. Why? Because A B whole inverse, that is equal to B inverse A inverse, right? So using this thing over here, we have x1 inverse x2 inverse is equal to x2 x1 inverse. So you see, because x1 was some member of G, x2 was some member of G, so therefore we also have their product, which is x2 x1 as a member of G, right? So therefore we have now expressed our C, where it is some member from G times A times the inverse of that some particular member, right, from G. So therefore C is expressed in this way, where this element is present in G, so we can clearly say C is related to A. So therefore this forms an equivalence relation under the group G, and hence we have the transitive property with us also. So now we once have the reflexive property, symmetry property, and the transitive property. We can clearly say this is an equivalence relation, and whatever is the set we obtain for A, which is nothing but the conjugacy class of A, that forms an equivalence class, right? So I hope you understood this proof well. Well, that is it for this video. Thank you for watching.